Okay, welcome back to the afternoon session. So the first talk is by Davide Trotta about abstracting sheafification like adjunctions by the tripos topos construction. It's 35 plus 10.
Perfect. Thank you very much, Don. Well, I'm back. First of all, I want to thank the organizers for the invitation, and I'm very glad to be here and to present this talk that is based on one work with Mini Maietti, so I want to take also this occasion to thank Mini for the contribution. Now, the main goal of this talk is to show how we can use the notion of tripos and the tripos to topos construction in order to abstract some sheafification-like adjunctions at the level of triposes. In particular, in the first part, I will present what I think is the main result of this talk, that is an abstraction of the ordinary sheafification, which is the case for the sheafification for localic toposes, to an arbitrary set-based tripos, and then to an arbitrary topos obtained as the tripos to topos construction for a set-based tripos. So, before starting with all the details, I would like to make a very short summary about the tripos to topos, the motivation, and present you what is the main goal and the main result that I want to present today. Now, let me recall just that the tripos to topos construction essentially is a generalization of a construction that is due to X. And well, it is a construction that takes a particular Lovier hyperdoctrine that is called a tripos as an input and produces a topos as an output. This is a proper generalization of the ordinary construction of the category of sheaves for a locale, because when we consider a tripos that we will call it this a localic tripos, which is a functor associated with a given locale. Well, if we apply the tripos to topos construction to these tripos, we obtain precisely the category of sheaves on a locale. And well, I think that one of the main motivations which are behind this construction is that essentially this offers an abstract tool to understand, for example, what are the common features from an abstract perspective of localic toposes and relativity toposes, because we know that these are very different families of toposes, but from an abstract point of view, both the relativity toposes and the localic toposes can be seen as instances of this construction. And now the main purpose of this first part is to show how we can use such a construction to abstract more properties that are typical of the, let me say, localic world to the general case of an arbitrary tripos. In particular, we know, for example, that if we have a locale, we can construct also another category, that is the category of presheaves on this locale, and we have an adjunction that is known as the sheafification. And well, if we want to abstract this sheafification for arbitrary triposes, the first problem is to, first of all, we have to abstract, to define a category that wants to be a generalization of this one for an arbitrary tripos. And well, the idea is that in the localic case, the category of presheaves can be presented as the exact completion of the glotemic category of this localic tripos. So this is a good shape, and using this presentation, it is easy to generalize this category for arbitrary tripos. And what I'm going to show is that if we start with a localic tripos, then we can construct this category. This is the sheafification because this is the category of presheaf. And well, what we have is that this category can be obtained as the result of the tripos to topos construction applied on this tripos, which is obtained by taking this and applying a free construction that is called the full existential completion. And by the universal properties of the completion, we have an adjunction between triposes here, and this induces an adjunction between the toposes, which is precisely the sheafification. And well, this picture can be generalized, not for every tripos, because in general we want to consider triposes with those base categories, not necessarily the category of sets, but for a family of triposes that we call with this name sheaf tripos, we can prove that all this picture can be generalized. And so for these sheaf triposes, we will see the definition later, what we can prove is that when we apply the full existential completion to this tripos, we obtain another tripos, and the tripos to topos construction is this one, this category, so having the same shape of this. We have an adjunction, and this induces an adjunction here that abstracts the sheafification. Finally, we will prove that any tripos whose base category is the category of set is in particular a sheaf tripos. So, for example, you can take this to be the relativity tripos, and what we will prove is that the every relativity tripos can be seen as a topos of sheaves for a certain Liouville-Tierney topology. So it is not according to topos, we already know that, but it can be seen as the category of sheaves for a certain Liouville-Tierney topology induced by this adjunction with respect to this topos, which plays the role of the topos of pre-sheaves for the locality case. So this is the main result that I'm going to present you today. And after this, we will consider some other two sheafification that we want to abstract in a similar idea. So first of all, we can start. I want to provide you some references. These are just the short list where you can find all the tools that are involved in the proof of our result. In particular, here you can find, of course, the definition of tripos and tripos to topos, also in this paper, where triposes are considered over an arbitrary base in the final product. Then we will need this result by Mandy, which is the characterization of categories whose exact completion is a topos. Then we will need the presentation of the tripos to topos as an exact completion of essentially elementary and existential doctrine presented in this work by Maietti and Rosolini. And then we need, in order to lift the adjunction between triposes to their tripos to topos, we need to use the careful analysis of the tripos to topos construction presented in this work, because the problem here, by Jonas, of course, because well, the problem here is that this arrow is just, we will see the definition later, a morphism of primary doctrines. And in general, so this means that this morphism does not preserve, for example, the existential quantifiers or the quality predicate. And in general, it is for these kind of arrows, well, it is difficult to lift these kind of arrows to their toposes. But since we have an adjunction whose left leg preserves all the regular structure, we can use the construction to induce another adjunction here. And
can I ask a question?
Sure.
Can you go back to the previous diagram?
Yeah.
It looks like it follows from your setup there that the lower right thing on the right-hand diagram, the Grothendieck, the lower right thing on the right-hand diagram,
yeah,
the Grothendieck construction of the tripos and then the x-lex completion is a topos.
Yeah.
Was that already known, that the x-lex completion of the Grothendieck construction, the category of elements of tripos, is a topos?
It is not true in general.
You just said it was.
It is true for all set-based triposes, but in general this is not true.
And the sheaf tripos is a sheaf subtopos of this gadget, even though the gadget itself is not in general, a topos?
Well, the problem is that when this is not a topos, we will see this later. If this category is not a topos, this is not a tripos, and then we cannot lift this adjunction, because this is crucial. We
Yeah,
cannot
it's
give this
crucial.
morphism to this one. So, of course, we can take a tripos, apply the construction. This will be just an elementary and existential doctrine.
Yeah.
This will be an exact category, but we will not have this adjunction.
Yeah, I'm less interested in going around the lower left than I am in going diagonally across. I take the category of elements for tripos.
So it's a sheaf tripos. That's an additional assumption that's written on the upper right corner.
Yeah.
It's a,
We need.
he's calling it a sheaf tripos, it's just a tripos.
No, but it's the definition of sheaf tripos is that this works.
Exactly.
If I take any tripos, I can take the category of elements. I can take the category of elements, the tripos P.
Yeah,
I can
of
take
course.
I
You
can
can take
take the
the.
X, that's completion.
Sure, but in
And
general,
I
this is
take the
not.
lower right-hand corner.
Sure.
I don't care if it's a tripos to topos of some other junk. I'm
Yes.
just asking about that category.
Yes, you can always take this category, but in general, it is not guaranteed that you have this adjunction with these tripos to topos, unless this is a tripos. I don't know if this answer to your question.
I think that's your theorem, which now clarifies
Yeah.
what you're telling
Yeah,
me.
yeah.
But
Yeah.
the adjunction always exists, doesn't it?
The adjunction always exists, yes, by the universal properties of. We'll see all this later, so I'm scoring all the talk now. But yes, this adjunction always exists. But the problem is that, for example, when this is just an elementary and existential doctrine, and this is another elementary and existential doctrine, we can of course construct these categories. This coincide with the this is exactly the tripos to topos construction. I will show the result later of this. But we cannot lift this adjunction to their exact completion. This is the problem, because this morphism does not preserve the regular structure. So we necessarily need the power object to do this, to lift this adjunction to an adjunction here. In the general case of elementary and existential doctrines, we have this picture that is the same, but these are not toposes. And we have just an arrow from here to here. This one, we don't know how we can lift.
But on the right, if you, as soon as you assume the P is a tripos, then it works.
Yeah, yeah,
even if it's
yes,
not sheaf tripos.
yes, yes. But this is not a topos. Yeah, yeah, yeah. Sure.
But in some cases, GPX is a topos, right?
And
In the realizability case,
it
if
is a
the
topos.
realizability tripos,
This is a topos.
yes, and then it will be the exact completion of the category of ascending.
No, this is very similar.
No, it's partition.
No.
It's partition.
No, this category indicates. Let me write. Indicates
It's a total category of tripos. It's more than a sentence.
Yes, but the difference is very small.
Yeah, okay.
This is an assembly, and while in the case of the growth, we just have predicates like this. So we admit also.
Yes, I know that. But the difference is quite small, and
Yeah.
and the exact completion will remove the difference. I think.
No,
I don't know. Maybe I wanted to ask this.
Anyway, I know that the exact completion of the category of ascending is a topos.
Yes. This I know this result.
Yeah. Yeah, it's in,
Yes.
it's a form of-
It has a name.
it's a
I
form
don't
of
remember now.
residential.
Yeah, but I don't know if it is the same category, because here we have more predicates, and I don't know if it is doing exact completion.
The one is.
I think that the fact is that this category, from an abstract point of view, we know that it is precisely the category of projective for the result of the total category, because of the result of Carboni. So assuming that the exact completion of assemblies.
I believe that it is.
But I think the non-empty power set and the power set are two different OPCAs. So they're two different
From
Okay, now the works, and now I can start to give the details. And I want just to quickly recall some standard definition. We already saw the tutorial by Pino, but let me just quickly fix the notation for today. In this talk, I will use these definitions of a full primary doctrine for a functor whose base category has finite limit, and this is of course a primary doctrine in the sense that we saw yesterday. So it is a functor from the opposite of a category into the category of insimilarity. The only difference is that I'm using here the word full to remind you that this has finite limits. And well, a full primary morphism of doctrine is then given by a pair, where the first component is a finite limit preserving factor, while the second component is a natural transformation to P into this composition. I will be quite quick on these notions. Similarly, we have the definition of full primary doctrine, and that is a full existential. In this case, we will say that a full primary doctrine is full existential, when for every arrow we have this functor. I'm using this notation to denote the functor obtained by applying the doctrine to this arrow as a left adjoint, and this satisfies the Beck-Chevalier condition for Vidi's reciprocity. And here you can find the notion of morphism of full existential doctrines. So this is a full primary morphism of doctrine, but we need to require that the second component commutes properly with the existential ground factors. Now, okay.
Sorry, what is your base category? That is final product.
Finite limits.
Limits.
Yeah.
Beck-Chevalier for all.
Yeah, for all pullets. Yeah, otherwise the theoretically has no limits, so we cannot perform the exact completion. And well, full existential doctrine is said to be full hyper doctrine whenever for every object this poset is an anything algebra, and for every arrow this functor is a morphism of anything algebras. And of course we need to require that for every arrow this functor has also right adjoint satisfying the Beck-Chevalier condition. So this is this is an hyper doctrine, but again I'm using full to record that the base category has finite limit. And well, a full hyper doctrine is said to be a full tripos if for every object X of the category there exists an object that I denoted in this way, and an element which is an element of this fiber, such that for every element alpha of this fiber there exists an arrow from this object into this one, such that alpha can be written in this way. So this is the notion of tripos, of full tripos. Again, we are considering just the general case where we have a category which can be an arbitrary category and not set. The only requirement is that this has to admit finite limits. Some examples: if we have a locale, we can construct the so-called localic tripos that sends a set into the poset of functions from that set to A with the pointwise order. This is a full tripos. And of course, we have the other example, which is well known, and is the case of realizability tripos. I don't want to recall all today, but I want to spend more minutes on another simple example. That is the case of the weak subobject doctrine, or doctrine of variations. In this case, we start with a category with finite limits, and we can define a functor denoted in this way, where essentially this poset is given by the poset reflection of this slice category. And again, the action of this functor on an arrow is given by taking the pullets, essentially. This is just a full existential doctrine in general. This is a full tripos if and only if the base category has weak dependent products and a generic proof. This is a notion that you can find in the paper of Manny, and this is essentially related to the fact that the tripos topos construction of this category coincide with the exact completion of the base category. We will see this example in another slide.
Yeah. The assumption of weak dependent products is stronger.
What?
The assumption of weak dependent products is stronger.
No, this is necessary for obtaining the structure of full hyper doctrine.
Is it if and only?
And if and only if you have that this is a full hyper doctrine whenever the base category.
Maybe I'm misremembering something. I thought
yes,
there was
you
a
can,
problem, but
because you can use weak dependent product to construct the the right adjoints, and then you can define the implication using this.
But the
And
question,
this is the complex.
question is whether you can use the pine implication to get weak pine products. And that, I think, there might be a problem. The other.
We can speak about this later, but I'm pretty sure that this should be an if and only if also for this
If and
case.
only if, because we have it also for elementary course completion.
I can,
We have a generalization.
Maybe.
Silly question, do you not need an image factorization to get the left adjoint of the existential structure? No?
no, this is not. Just a
For
category.
this, no.
For this, we just need a category defining the limits. You can define this one. And for having the tripos structure, we need to require these two conditions.
It's just many reformulated.
Yes, it's just a reformulation of the result of many in terms of doctrines.
It's just many, just very similar.
Because the characterization of many was on if and only if. So you can translate that in the language of doctrine and you can obtain this. But we can speak about this later. Now, as I said, the first thing that we have to define if we want to generalize the starting picture is, okay, well, we know to define a category which wants to be the category of presheaves of our tripos. And to define this category, I want to recall the notion of broadening category associated with a full tripos. Well, essentially, if we have full tripos, we can define this category, denoted in this way, and the objects are pairs, where the first component is an object of the base and the second one is an element of this fiber. And a morphism is just an arrow of the base satisfying this condition.
The definition.
With this notion, we can define a category that wants to be a generalization of the category of presheaves for an arbitrary tripos, as I said at the beginning. So, given a full tripos, we can define the category of P presheaves as the exact completion of the Grothendieck category. Again, as I said, this in general is not a topos. It's just an exact category. If the tripos has, if the base category is the category of sets, we will see that this is always a topos, but in general, this is not. This is just an exact category. Some examples, again, in the locality case, we know that we have this equivalence, so the category of presheaves for a locale can be seen as the exact completion of the co-product completion of the locale, but this is precisely the Grothendieck of the locality tripos. It is exactly the same category. And well, this is the case for the realizability tripos, so this is very similar, it's very close to be the category of assemblies, as we said, the Grothendieck category is very close to be the category of assemblies, but the only difference is that we admit also that the function can be empty on some certain points. Okay. Now we have seen how we can define a category, a generalization of the category of presheaves. Now I want to just quickly recall the two constructions that we need to produce the initial picture, which are the tripos to topos construction and the full existential completion. Again, I have no time to provide all the detail, but let me just give you an idea. Well, if we have a full tripos, we can define a topos in this way, using this notation. The object of this category are pairs where this is an object of the base, and this is essentially a relation satisfying these two conditions. And now, an arrow in this category is essentially an object, so a relation, which wants to be functional and entire and total with respect to these two relations. So this is the roughly speaking, the idea.
I mean, this is different from what I wrote yesterday, but is this deliberate? That the first, I mean, phi AB should imply rho AA.
What?
But phi AB should imply rho AA, no? In the first line of here.
Maybe I use another order in presenting the action.
No,
But it doesn't really matter.
no, it's correct.
This is the one from the. Yeah.
Okay, it's that detail.
Okay, the other construction, again, I want just to give you an idea, is the full existential completion, that is a free construction that freely adds left adjoints to a given doctrine. And The idea is that we can take a full primary doctrine and we can construct a new doctrine on the same base category, and we use this notation to denote this new doctrine. And this new doctrine has left adjoints along all the morphisms. Here there is the explicit construction. The idea is that an object of a fiber like this represents this formula. This is the idea. And well, the important fact is that we can freely add left adjoints along all the morphism of the base to a given doctrine, obtaining a full existential doctrine from a full primary one. The problem is that this construction in general does not preserve the tripos structure. There are just some cases in which the tripos structure is preserved. Now we have some examples, which are these two are triposes. These two triposes are instances of the full existential completion. The locality doctrine is an instance of the full existential completion if and only if the locale is a supercoherent locale. So for an arbitrary locale, we have that the locality tripos is not full existential completion, but when the locale is supercoherent, yes, this is the case. That this tripos is again this is a full existential completion. The Wix of object doctrine for a given Lex category, again, this is a full existential completion of a trivial doctrine. Let me say that is the doctrine that is a doctrine that takes an object and sends it into the positive with just the top element. If you apply the full existential completion to this, this trivial doctrine, we obtain precisely the Wix of object doctrine. Okay, now the first result is that when P is a full tripos, and if this is a full existential completion of full primary doctrine, then the tripos to topos is equivalent to the exact completion of the Grothendieck category of this doctrine. So the doctrine which is essentially the doctrine of generators for this full existential completion. Again, so what we have is that, for example, these categories can be all obtained by combining the full existential completion and the tripos to topos. For example, in the case of realizability toposes, we have that the Grothendieck category of the generators is precisely the category of partition assemblies. For what we saw before, we have that every pre-shift category for a given locale can be obtained by applying the full existential completion plus the tripos to topos to a locality tripos, while this category can be presented in this way only in the case the locale is supercoherent. And finally, we have that exact completion on the next category is again an instance of these two constructions. Now we have the main definition and the main one of the main results. But what we have is that we will say that a full tripos is a shift tripos if the Grothendieck category has weak dependent products and a generic truth. For when a full tripos is a shift tripos, we have that these conditions are equivalent. In particular, P is a shift tripos, the Wix of object doctrine is a full tripos, the existential completion is a full tripos, and this is a topos. These are equivalent. And for shift triposes, we have exactly the picture that I presented at the beginning. So if P is a shift tripos, then there is an adjunction of triposes, such that this composition is identity, and this morphism is a full existential morphism. So this preserves all the structure of the full existential doctrine. And of course, we have that this adjunction induces an adjunction between the tripos to topos construction applied to this one and the tripos to topos construction applied to this one. And again, we have that this composition is identity. Corollary, if P is a sheaf tripos, then there exists an WDF23 topology on the tripos to topos associated with the full existential completion of P, such that the tripos to topos construction of the original tripos can be presented as the topos of sheaves with respect to this WDF23 topology for these topos. This is a direct corollary of the previous result. Now, the problem is that if we want to concretely check if the growth category of tripos has weak dependent product and generic proof, well, it is quite, at least for me, it is quite hard because in the growth category we have two different structures that are mixed. So, in order to apply this result and in order to find more examples, we provide some sufficient conditions where essentially we wanted to keep the structure of the base category and the structure of the fibers in two different separated divided, because these, as we will see, these are more easy to check for concrete cases. In particular, what we have is that if P is a full tripos such that the base category has weak dependent products, the weak predicate classifier has a power object in C, and the base category admits a proper factorization system and every AP of this class splits, then this is a sheaf tripos. You will see that this is a condition on the base. It does not depend on any structure of the fibers. This again is a condition on the base, and this the only fact is that we need to take the weak predicate classifier and the power object of the base category. So these are easier to check. As a corollary, we have in fact that every full tripos whose base category is set, assuming the axiom of choice, is a sheaf tripos. And so we have that as the ordinary sheafification can be presented as a particular case of our result, but also for the readability triposes, we have this adjunction where this category is precisely the exact completion of the growth decay category associated with the tripos. Now, I have the time for just one extra sheafification like adjunction. And well, we know that for readability toposes, set, the category of set can be presented as a category of sheaves for the readability topos. But the problem is that, more generally, are we able to find a connection between the base category of a tripos and the tripos to topos construction of this tripos? And well, the fact is that if we have a full tripos arising as full existential completion, whenever the base category has weak dependent products and a generic proof, then we have an adjunction of triposes between this, that is the tripos, the weak subobject doctrine, and it is a tripos because we have this assumption. So we have an adjunction here, such that this composition is identity. And now we have that both these arrows are full existential morphism. And then we can abstract, we can apply the tripos to topos construction, obtaining that whenever P is a tripos satisfying this condition, the exact completion of the base category can be seen as a category of sheaves for this, with respect to a certain WDF23 topology for this topos. In the case of set-based tripos, we know that the exact completion of set is set again, so we obtain the usual presentation of set as a category of sheaves for readability toposes. And here this is the corollary, and this is the example for readability toposes and set. And in the localic case, again, we have that this result can be applied only for localic triposes, where the locality is super coherent. And now I think that it's time to stop for me. So thank you very much for your attention.
think I was a bit sleepy in the moment. I could not remember what the full tripos is, or the full hyperduction.
It is a tripos, and I just use the word full because I want to. It is a tripos was base category as finite, nothing more.
And the base category has finite limits, and the Beck-Chevalier condition holds always full limits.
Is that full? It has nothing to do with full and phase fit.
No. It's just a name for because I want to remind the fact, to stress the fact that the base category has to be with the finite limits.
Ah, okay, thank you.
Yeah. You will see. Yes, and we have Beck-Chevalier along
Full range of
yeah.
Do you have a better name?
No, I would have to think about it. But full for me meant, yeah.
It's wrong.
You don't get, so in your construction of the XLX completion plays a big role.
Yeah.
So what about the reg legs or the X-reg completions?
Okay, I see. Yes, I see. Well, if we have a full tripos and we apply. If we have a full tripos P, and we can apply the regular completion of this doctrine, you can find this is a result by Lili and Pino, and so we can obtain this category that is regular and Fabio. And when this is the full existential completion of another doctrine, then this is precisely.
And that was not the
This was
What did you ask?
the reglex
What did
completion.
you ask?
Yeah, well,
Of-
if you think that it's considered the reg legs completion.
Reglex, right?
Ah,
Reglex.
yes,
Yes.
this is a basic.
In fact, we obtain the characterization of the exact completion as a corollary of this one.
Yes,
But I
this
didn't
is
present
the-
this one. I won't just present exactly the completion today because.
Yeah.
No, but I mean, what you can do is that you start with an arbitrary tripos,
Yeah.
with a sheaf tripos, and you take the reglex completion of the total category.
The reg. Ah,
It's the same, we have the same.
it is the same. It is
The
the
same,
same.
we have the regular.
Because the fact is that we first characterize the regular, the case of the regular completion, and then the case of the exact.
The exact completion is a
Is a corollary of this characterization for the.
But here you're assuming that it's
That this is this tripos is not necessarily a shift tripos, but this has to be a full existential completion of this.
Yeah,
But like in the final case, in the final slide.
but yeah, I believe if you take the regular completion of the total category for sheaf tripos, but you get something between your free sheaf tripos and your pre-sheaf topos and your sheaf topos.
The total category.
Yeah.
Yes, probably yes.
Connecting with the X-reg.
Yeah.
The X-reg
Yeah.
of the regular reglex is the X-lex. Is the leg.
Exactly.
Yeah.
Yes,
Yeah.
yes, indeed, this is the composition, because
Yes.
this is the key one.
And I think it might be the Q topos, so the quasi topos that we get.
This
No,
would be
the
nice
Q,
to-
no, the quasi-topos is another part. It's another one. Separated objects.
Yeah. Any more questions? Yeah. Yeah, Raphael.
Okay, thanks. Yeah, so I can't help but to naively draw parallels to what I will talk about tomorrow myself. Many of these notions I haven't seen before, so just because they sound and look similar, I will ask if there are connections. Namely, your assumption of having weak dependent products, I don't exactly know what that means, but so that's
Okay.
part of the
For me, the weak subobject doctrine is a full hyper doctrine. This is another way to see it.
Yeah.
This. Okay.
I wouldn't know how to decode that
It doesn't.
on the spot. So, and having a generic proof.
Yeah.
So if I look at the Grody construction you construct from it, right, which is fibered over C, basically,
Yeah.
right? Is that in any way connected to that vibration being locally small and having a generic object in the sense of Thomas Schleicher's talk earlier today, which would mean that it comes from an internal locale or something like
I'm
that.
not sure. I'm not sure that there
I
is.
don't know where.
So it would mean that, so we have the Grody construction fiber over C, so
Yes, it is.
vibration. And then this vibration can be locally small, right? There's a definition of it being locally small, as we saw earlier today. And there's a definition of being globally small, which means in one category theory to have a generic object. And I would think that this generic proof you assume is a generic object for that
Maybe yes,
vibration.
but I admit that now I don't know how to make the connection in detail. But
Thank you.
thank you for.
Any more questions? Matteo, you had a question? No.
But,